electrical circuits, the ground wire must be protected from physical damage, just like the hot and neutral wires. All three wires should be within the outer sheath of a cable assembly such as Romex. This requirement is crucial for several reasons. Firstly, physical protection ensures the integrity of the ground wire. Damage to the ground wire can compromise its ability to provide a safe path for fault current, increasing the risk of electrical shock or fire. Secondly, the National Electrical Code, or NEC, mandates that all circuit conductors, including the ground wire, be protected from physical damage. This protection is typically achieved by enclosing the conductors within a raceway, cable assembly, or other approved means. Thirdly, the outer sheath of a cable assembly like Romex provides a barrier against abrasion, moisture, and other environmental factors that can degrade the insulation and conductivity of the wires. This helps to maintain the reliability and longevity of the electrical system. When installing electrical wiring, it is essential to follow the NEC guidelines and manufacturer's instructions for proper installation and protection of all conductors. This includes ensuring that the ground wire is properly sized, connected, and protected from physical damage. Failure to do so can result in serious safety hazards and code violations. Grounding is a critical safety measure in electrical systems, providing a low impedance path for fault current to return to the source. This helps to quickly trip a circuit breaker or fuse, de-energizing the circuit and preventing electrical shock or fire. The ground wire also helps to stabilize the voltage on the electrical system, reducing the risk of voltage fluctuations and surges. In addition to physical protection, the ground wire must also be properly sized to handle the maximum fault current that it may be subjected to. The size of the ground wire is typically determined by the size of the circuit conductors, as specified in the NEC. It is also important to ensure that the ground wire is properly connected to the grounding electrode system, which provides a connection to earth. The grounding electrode system typically consists of a ground rod, ground plate, or other approved grounding electrode that is buried in the earth. The connection between the ground wire and the grounding electrode system must be made with a listed grounding connector. Furthermore, the ground wire should be continuous and unbroken throughout the entire circuit. Any splices or terminations in the ground wire must be made with approved connectors and must be accessible for inspection and maintenance. The ground wire should also be protected from corrosion. Corrosion can increase the resistance of the ground wire, reducing its ability to carry fault current. To prevent corrosion, the ground wire should be made of a corrosion-resistant material such as copper, or it should be protected with a corrosion-resistant coating. The NEC provides detailed requirements for grounding and bonding in electrical systems. These requirements are designed to ensure the safety and reliability of electrical installations. It is important to consult the NEC and other applicable codes and standards before installing any electrical wiring. Electrical work can be dangerous, and it should only be performed by qualified and licensed electricians. It is also important to regularly inspect electrical wiring and equipment for signs of damage or wear. Any damage to a worn wiring or equipment should be repaired or replaced immediately. By following these guidelines, you can help to ensure the safety and reliability of your electrical system. Grounding systems serve several crucial functions in electrical installations. 1. They provide a low impedance path for fault currents, facilitating the rapid operation of overcurrent protection devices like circuit breakers or fuses. This swift action minimizes the duration of fault conditions, reducing the risk of electrical shock, fire, and equipment damage. 2. Grounding systems help stabilize voltage levels within the electrical system. By providing a reference point at earth potential, they mitigate voltage fluctuations and transient surges, protecting sensitive electronic equipment from damage. 3. Grounding minimizes electrical noise and interference. By providing a path for stray currents to return to the source, it reduces electromagnetic interference that can disrupt the operation of electronic devices. 4. Grounding provides a safe path for static electricity to discharge. Static electricity can accumulate on equipment and personnel, creating a risk of electrical shock or damage to sensitive electronics. A properly grounded system allows static charges to dissipate safely to earth. The NEC mandates specific requirements for grounding and bonding to ensure safety and proper system operation. Some of these key requirements are 1. Grounding electrode system. All electrical systems must be connected to a grounding electrode system, which typically consists of a ground rod, crown plate, or underground metallic water pipe. The grounding electrode system provides a direct connection to earth, ensuring a low impedance path for fault currents. 2. Equipment grounding conductor. An equipment grounding conductor, or EG, must be installed with all circuits to provide a path for fault currents to return to the source. The EGC is typically a bare or green insulated wire that runs along with the circuit conductors. 3. Bonding. All metal parts of the electrical system, including enclosures, raceways, and equipment, must be bonded together to create a continuous electrical path. Bonding ensures that all metal parts are at the same potential, reducing the risk of electrical shock. 4. Grounding electrode conductor sizing. The size of the grounding electrode conductor, which connects the electrical system to the grounding electrode system, must be sized according to the NEC tables based on the size of the service entrance conductors. 5. Equipment grounding conductor sizing. The size of the equipment grounding conductor must be sized according to the NEC tables based on the size of the overcurrent protection device protecting the circuit. 6. Continuity. The grounding system must be continuous and unbroken throughout the entire electrical system. Any splices or terminations in the grounding conductors must be made with approved connectors and must be accessible for inspection. 7. Protection. Grounding conductors must be protected from physical damage. This can be achieved by enclosing the conductors in raceways or using cable assemblers with a protective sheath. 8. Identification. Grounding conductors must be clearly identified. Equipment grounding conductors are typically green or bare, while grounding electrode conductors are typically bare. Regular inspection and maintenance of grounding systems are crucial to ensure their effectiveness. Some common maintenance tasks include 1. Visual inspection. Visually inspect all grounding conductors, connections, and electrodes for signs of damage, corrosion, or loose connections. 2. Continuity testing. Use a multimeter to test the continuity of the grounding system, ensuring that there are no breaks or high resistance connections. 3. Ground resistance testing. Use a ground resistance tester to measure the resistance of the grounding electrode system. The resistance should be within acceptable limits, as specified by the NEC. 4. Tightening connections. Tighten all grounding connections to ensure that they are secure and provide a low resistance path for fault currents. 5. Corrosion prevention. Protect grounding conductors and connections from corrosion by applying a corrosion-resistant coating or using corrosion-resistant materials. 6. Record keeping. Maintain records of all grounding system inspections, tests, and maintenance activities. These records can be used to track the performance of the grounding system over time and identify any potential problems. Failure to properly install and maintain grounding systems can have serious consequences, including 1. Electrical shock. A faulty grounding system can increase the risk of electrical shock, which can be fatal. 2. Fire. A faulty grounding system can cause electrical faults to ignite flammable materials, leading to a fire. 3. Equipment damage. A faulty grounding system can damage sensitive electronic equipment due to voltage surges and electrical noise. 4. Code violations. Failure to comply with NEC requirements for grounding can result in code violations, which can lead to fines and other penalties. In summary, grounding is a critical safety measure in electrical systems. By providing a low impedance path for fault currents, grounding helps to protect people and equipment from electrical hazards. It is essential to follow the NEC requirements for grounding and bonding and to regularly inspect and maintain grounding systems to ensure their effectiveness. The purpose of the ground wire, also known as the equipment grounding conductor, is to provide a low impedance path for fault current to return to the source in the event of a ground fault. A ground fault occurs when a live conductor comes into contact with a grounded metal part of an electrical system, such as the enclosure of an appliance or piece of equipment. Without a ground wire, the fault current would have no easy path to return to the source, and the voltage on the grounded metal part could rise to a dangerous level, creating a risk of electrical shock. The ground wire provides a low impedance path for the fault current to flow back to the source, which causes the circuit breaker or fuse to trip, de-energizing the circuit and preventing electrical shock. The ground wire also helps to equalize the voltage potential between different metal parts of the electrical system, reducing the risk of electrical shock. All metal parts of the electrical system that are likely to become energized must be bonded together and connected to the ground wire. This includes metal enclosures, raceways, and equipment. Bonding ensures that all metal parts are at the same potential, so that if a fault occurs, the voltage on all metal parts will rise to the same level, reducing the risk of electrical shock. The size of the ground wire is determined by the size of the circuit conductors. The NEC provides tables that specify the minimum size of the ground wire based on the size of the circuit conductors. The ground wire must be large enough to carry the maximum fault current that it may be subjected to. The ground wire must be continuous and unbroken throughout the entire circuit. Any splices or terminations in the ground wire must be made with approved connectors and must be accessible for inspection and maintenance. The ground wire must also be protected from physical damage. This can be achieved by enclosing the ground wire in a raceway or using a cable assembly with a protective sheath. The ground wire must be connected to the grounding electrode system. The grounding electrode system provides a connection to earth. The grounding electrode system typically consists of a ground rod, ground plate, or other approved grounding electrode that is buried in the earth. The connection between the ground wire and the grounding electrode system must be made with a listed grounding connector. Grounding is a critical safety measure in electrical systems. By providing a low impedance path for fault current to return to the source, grounding helps to protect people and equipment from electrical hazards. It is important to follow the NEC requirements for grounding and bonding and to regularly inspect and maintain grounding systems to ensure their effectiveness. The NEC specifies the requirements for the physical protection of ground wires in Article 250. Specifically, Section 250.120 addresses the mechanical protection of grounding conductors. It states that grounding electrode conductors and grounding and bonding jumpers shall be protected from physical damage by enclosing them in rigid metal conduit, intermediate metal conduit, rigid non-metallic conduit, electrical metallic tubing, cable armor, or other means. The type of protection required depends on the location and environment in which the grounding conductor is installed. In general, grounding conductors that are exposed to physical damage, such as those run along the exterior of a building or in a damp or corrosive environment, must be protected by a more robust means, such as rigid metal conduit. Grounding conductors that are installed in a less exposed location, such as within a wall or ceiling, may be protected by a less robust means, such as cable armor or electrical metallic tubing. The NEC also requires that grounding conductors be protected from corrosion. This can be achieved by using grounding conductors that are made of a corrosion-resistant material, such as copper, or by coating the grounding conductors with a corrosion-resistant coating. In addition to the NEC requirements, local codes and regulations may also specify requirements for the physical protection of ground wires. It is important to consult with a qualified electrician or electrical inspector to determine the specific requirements for your location. The consequences of not properly protecting ground wires from physical damage can be severe. If a ground wire is damaged, it may no longer be able to provide a low impedance path for fault current to return to the source, which can increase the risk of electrical shock or fire. Therefore, it is essential to follow the NEC and local code requirements for the physical protection of ground wires to ensure the safety of people and property. Remember to always consult with a qualified electrician for any electrical work. Firstly, the function of a ground wire is to provide a safe path for electrical current in the event of a fault. Secondly, protecting the ground wire ensures that it can perform its function effectively. Thirdly, physical damage to the ground wire can compromise its ability to carry fault current. Fourthly, the NEC requires that ground wires be protected from physical damage. Fifthly, the type of protection required depends on the location and environment in which the ground wire is installed. Sixthly, grounding conductors must also be protected from corrosion. Seventhly, failure to properly protect ground wires can increase the risk of electrical shock or fire. Eighthly, consult with a qualified electrician or electrical inspector for specific requirements. Ninthly, grounding is essential for the safety of electrical systems. Tenthly, always prioritize safety when working with electricity.